Hello and welcome to a lesson on geometric progressions. In this lesson, we'll define what a geometric progression is, we'll identify the parameters that characterize a particular progression, and we'll derive formulae for finding the nth term, the sum to n terms, and the sum of an infinite number of terms. Once we've done all that, we'll tackle a range of questions typical of those found on A-level exam papers on this topic. To begin then, let's have a look at an example. 6, 12, 24, 48, 96 and so on. A geometric progression, you obtain one term from the previous term by multiplying by a fixed constant. So we can see here that 12 is obtained from 6 by multiplying by 2. 24 is obtained from 12 by multiplying by 2. And we call that the common ratio, what we multiply by each time. So the two numbers that characterize this geometric progression are the first term, 6, and the common ratio, 2. Once we know those two numbers, we can find anything we need to know about this geometric progression. So in general, the first term we call A, much like we did on the arithmetic progressions. The second term is A multiplied by the common ratio R. Now we just keep multiplying by the common ratio R to find the next term. So the third term is AR squared. AR multiplied by R. The fourth term will be AR cubed. Now then, what would the nth term be? Well, if we look at these closely, we see that the power of R is 1 less than the number of the term, because there's no R in the first term. So in the third term we've got AR squared, in the fourth term we've got AR cubed, in the nth term we'll have AR to the power n minus 1. So that's the formula for the nth term in a geometric progression. We'll now go on to look at deriving a formula to find the sum of the first n terms. So let's consider Sn, the sum of the first n terms. It will be A plus AR squared plus AR cubed and so on, all the way up to the nth term, which we've already decided is AR to the n minus 1. So the one before that, for instance, would be AR to the n minus 2, 1 less in the power of R. We'll call that equation 1. Now, let's multiply by R. Multiply that whole equation through by R. So on the left-hand side we've got R times Sn, and on the right-hand side the power of R in each term has been increased by 1. So instead of starting with A, we start with AR. AR becomes AR squared becomes AR cubed, and so on. The second last one will have AR to the n minus 2 becoming AR to the n minus 1. And the very last term, the nth term, will be AR to the n, because we've multiplied AR to the n minus 1 by another R. What we're going to do now is subtract equation 1 from equation 2. So let me write down what that gives us. On the left-hand side, we've got RSN minus Sn. So that's RSN minus Sn. But what will we have on the right-hand side if we take the top line from the bottom line? Well, this AR taken away from this one will disappear. And we'll find that most of these terms will cancel out. There'll be an AR to the 4 there that's amongst the dots, which will cancel that one out. And here this AR to the n minus 2 will be cancelled out by 1 there. They cancel out when the subtraction takes place. And the only two terms on the right hand side that don't cancel out are this one, because there's no AR to the n to take away from it, and this one, which is subtracted, but there isn't an A term to subtract it from. So basically, the right-hand side becomes AR to the n, from this line we're subtracting from, minus A. And we can simplify that. We can say that's r minus 1 lots of Sn is equal to, take out the common factor of a, and we've got r to the n minus 1. And then we can say the sum to n terms is equal to a r to the n minus 1 divided by this bracket here, divided by r minus 1. So we now have a formula for the sum of the first n terms. An alternative version of that is if we multiply the top and bottom by minus 1, we can have the brackets with the terms round the other way. 1 minus r to the n divided by 1 minus r. And that doesn't change the overall value, we've just multiplied the top and bottom by minus 1. Why would we do that? Well, typically if the ratio is greater than 1, we tend to use this formula, which keeps everything positive. And if the ratio is less than 1, we tend to use this formula, which again keeps the denominator positive. We can now have a look at finding the sum to infinity for a geometric progression, sometimes called a geometric sequence. And I'm using the second version of the formula we've just derived. Sn equals a multiplied by 1 minus r to the n over 1 minus r. Now this sum to infinity only holds true if the modulus of r is less than 1. So basically if r is trapped between 1 and minus 1. Because if the modulus of r is less than 1, then r to the n tends to 0 as n tends to infinity. So an example there would be if r was a half. A half squared is a quarter, a half cubed is an eighth, and it gets smaller and smaller and smaller, tending to 0 as n tends to infinity. Now if that's the case, we call the sum to n terms as n approaches infinity, we call it S infinity. And if we look how this formula will simplify, on the top r to the n becomes 0. So we have a multiplied by 1 minus 0, and on the bottom we still have 1 minus r. So that gives us our sum to infinity. 1 minus 0 is 1, 1 times a is a, so it's simply a divided by 1 minus r. And that completes what we need to know. Let's have a look at a summary of the properties of geometric progressions. The first term we call a. The common ratio we call r. The nth term we found was a r to the power n minus 1. The sum to n terms is a multiplied by r to the n minus 1 over r minus 1, but we can reverse both brackets and still have the same formula. And finally, the sum to infinity is a over 1 minus r, but it only exists if the modulus of r is less than 1. We're now ready to go on and tackle some A-level type questions. Right, we've got 6 examples to work through. We'll start fairly easy and gradually work our way through the different kinds of questions that occur on A-level papers. Example 1. For the geometric progression 5, 15, 45, 135 and so on, find the 8th term and the sum of the first 6 terms S6. Well, the things we need to know are A and R, and I can see that A, the first term, is 5. The common ratio is 15 divided by 5. If you divide one term by the previous term, that will always give you the ratio. 15 divided by 5 is 3. So the common ratio is 3. Now I want the 8th term. Now the nth term is AR to the n minus 1. So the 8th term is AR to the 8 minus 1, which is AR to the 7. So I just have to work out on my calculator 5 multiplied by 3 to the power 7. And that comes to 10,935. Next we want to find S6, but I'll begin by writing down Sn. Sn is equal to A bracket r to the n minus 1 divided by r minus 1. Substituting the values for A, R and N, and we get Sn, or S6 in this case, is equal to 5 multiplied by 3 to the power 6 minus 1 divided by 3 minus 1. And if we enter that in our calculator, we get a final answer of 1,820. And that concludes example 1. Example 2. For the geometric progression 40, 8, 1.6, 0.32, find the sum to infinity, S infinity. Well, again, we're going to need A and R. A, I can see, is 40, the first term. R, if I divide 8 by 40, that will give me R. Why does that work? Well, 8 is AR, 40 is A, and AR divided by A is just R. 8 40ths I could cancel to a fifth, or if you prefer, you could write it as a decimal 0.2. Now, S infinity is equal to A over 1 minus R. It exists because R is less than 1. A over 1 minus R is what we're trying to find. So if we put in the value 40 for A, that's going to be divided by 1 minus 1/5. Now, as I said, you could be straight into using your calculator here, but I do it mentally and say 1 minus 1/5 is 4/5, so this is 40 divided by 4/5. And to divide by a fraction, you turn upside down and multiply, so it's 40 multiplied by 5 over 4. 4 cancels into 40 10 times. 10 times 5 is 50, so that's the answer. S infinity is equal to 50. Example 3. The third term of a GP is 18, and the eighth term is 4,374. Find the sum of the first 10 terms. This is a very common question at A level. They give you any two terms of the GP, and using those two terms, you're able to find A, the first term, and R, the common ratio. How do we do it? Well, we write down the information that we're given. We're given information that the eighth term, which is A R to the power 7, is equal to 4,374. And we're told information about the third term. Now the third term is AR squared, and we're told that that is 18. And it doesn't matter which two terms we're given, the technique is always the same. What we do is we divide one equation by the other. So if I divide the top one by the bottom one, we get AR to the 7 divided by AR squared is equal to 4,374 divided by 18. Now the a's cancel, and r to the 7 divided by r squared is r to the power 5. And 4,374 divided by 18 turns out to be 243. And whichever two terms you're given, you'll always end up with a power of r here. Once you've divided, the a's will always cancel out. So r is simply the fifth root of 243, which I can write as 243 to the power 1/5. Put that in the calculator and r turns out to be 3. Fifth root of 243 is 3. Now we can substitute for that in one of these original equations to find a. So let's say substitute in AR squared equals 18, and we get A times 3 squared equals 18. Now 3 squared is 9, so that's 9A is equal to 18. So A is equal to 2, 18 divided by 9. And there's the two values we need, A and R. And we're now going to find the sum of the first 10 terms. So let's first of all write down Sn is equal to A R to the n minus 1 divided by R minus 1. And then put in the values for A, R and n, and we get S10 is equal to A is 2, R is 3, so that's 3 to the power 10 minus 1, and on the bottom R minus 1 is 3 minus 1. And if we put that in our calculator, we end up with 59,048. And that concludes example 3. Example 4. The first term of a GP is 60 and the sum to infinity is 100. Find the common ratio. Let's write down what we know. A is equal to 60. S infinity, the sum to infinity, which is A over 1 minus R, we're told that that is 100. So once I substitute 60 in for A, the only unknown will be R. So the implication is that 60 over 1 minus R is equal to 100. Multiply the equation through by 1 minus R and we get 60 is equal to 100 multiplied by 1 minus R. Expand the bracket and we get 60 is equal to 100 times 1 is 100, and 100 times minus R is minus 100R. So I'll now bring the R's to the left where they'll become positive, and I'll take this 60 to the right where it'll become negative. So that will give me 100R on the left is equal to 100 minus 60. So 100R is equal to 40. R is 40 divided by 100. So R equals 0.4. Of course it has to be less than 1 or between 1 and minus 1, otherwise there wouldn't be a sum to infinity. So that's the answer. R is equal to, common ratio R is equal to 0.4. Example 5. The first term of a GP is 4 and the common ratio is 7. Which term is the first to exceed 100,000? So we've been told that A is equal to 4 and R is equal to 7. Well, let's suppose this first term that exceeds 100,000 is the nth term. So let nth term be the first to exceed 100,000. Well, the nth term is AR to the n minus 1. So AR to the n minus 1 has to be bigger than 100,000. And it has to be the first one that's that big. So we'll get an inequality in n. And that's what I'm trying to find, n, because n is the first term exceeding 100,000. Let's put the numbers in that we know. A is 4, so it's 4 multiplied by 7 to the power n minus 1 has to be greater than 100,000. And now I'll just divide this inequality through by 4. So I'll get 7 to the n minus 1 on the left is greater than, and 100,000 divided by 4 is 25,000. Now at this point I'm going to offer you two methods. First of all, we can use trial and error, and secondly we can use logarithms. So let's start with the trial and error method. So method 1, trial and error. So we have a guess basically. 7 to what power is bigger than 25,000? Let's try 7 to the power 10. And if we work that out on the calculator, it comes to 282,475,249. So that wasn't a very good first guess, but it doesn't matter. If that's too big, let's come down and try 7 to the 5. 7 to the power 5 turns out to be 16,807. So that's not bigger than 25,000. The next one will be though, 7 to the power 6 is 117,649. That's just 7 lots of 16,807. So this one is less than 25,000. And this one is greater than 25,000. So that's when the inequalities become true. We've gone past the 25,000, so it means that 6 must be this n minus 1. So n must be 6 plus 1. So n is 7. So it's the 7th term that is the first one to exceed 100,000. Now let's try and establish this relationship using logarithms. 7 to the power n minus 1 has to be greater than 25,000. Well, what we can do is just take logs of both sides. So we get the log of 7 to the power n minus 1 is greater than the log of 25,000. And here I'm using logs to the base 10. Now, using our laws of logs, the log of 7 to some power is the power times log 7. So that's n minus 1 times log 7 is greater than log 25,000. Which means that n minus 1 is greater than log 25,000 divided by log 7. And if we put that into the calculator, we end up with n minus 1 is greater than 5.2. Which means that n is greater than, take the 1 the other side becomes positive, n is greater than 6.2. But n is a whole number, so n must be 7. That's the first term that exceeds 100,000. So we can finish by saying 7th term exceeds 100,000. Example 6, our final example in this lesson. In the GP 3, 6, 12, 24 and so on, how many terms are required for the sum to exceed 1 million? So it's not a specific term we want bigger than a million, it's the sum of the first n terms. So let's write down what we've got and what we want. We've got the fact the first term is 3, and we also know that r is 2. 6 divided by 3 is 2. And we want Sn to be greater than a million. So putting in the formula for Sn, we want a r to the n minus 1 divided by r minus 1 to be greater than a million. Now we put in the values for a and r. So we get 3 multiplied by 2 to the n minus 1 divided by 2 minus 1 is greater than a million. Now 2 minus 1 is just 1, so I'm looking at 3 times the bracket is greater than a million. Let's divide by 3, and then on the left hand side it's just 2 to the n minus 1, and that will be greater than a million divided by 3, 333,333.3, say. Take the one the other side and we get 2 to the power n has to be greater than 333,334.3. Two methods again, first trial and error and then logs. So we'll try trial and error first. Let's have a guess at 2 to the power 12. Put that in the calculator, turns out to be only 4096. So let's get further up the scale, 2 to the power 16. 2 to the 16 is 65,536, not big enough. Let's try 2 to the 18, and that gives us 262,144. Not quite there yet, but the next one's going to go beyond that, so 2 to the power 19 is equal to 524,288. So that's the first time that we've exceeded the target of 333,334. So 19 equals n. 19 terms required. Right, now let's achieve the same answer using logarithms. So I want 2 to the power n to be greater than 333,334.3. And what we do is we take logs of both sides. So the log of 2 to the power n will be greater than the log of 333,334.3. Now with laws of logarithms, the n comes to the front and we write that as n log 2. N log 2 will be greater than the log of 333,334.3. And so n will be greater than the log of 333,334.3 divided by log 2. And if we stick that in the calculator, the answer we get is 18.3. So n is greater than 18.3. But n is a whole number, it's the number of a term. So n must be 19, which is the same answer we got using trial and error. The choice is yours. Well, that concludes this lesson on geometric progressions, and there'll be an exercise to give you lots of practice at the techniques we've been covering.